will be how far it goes back up, and that will be my oscillation.
Is that always true? Really?
Yes,
Oh.
yes. There's no difference. Once you let it sit there and then you start it, there's no difference then between that and uh, a spring on a horizontal plane. But if we were to say that was our equilibrium point, then we're going to have problems, right? Because then it would just go like that, and it would bounce up a little bit and come back.
So when we're trying to find force for a vertical one, do we just add the normal force that happens because it's a spring, and then the force due to gravity?
Yeah, it'll still the excursion here, the restoring force will still follow the same formula. The F equals negative kx.
But don't you have to add in gravity?
No. Not as far as, well, yeah, as far as the force goes, you do,
Yeah.
but the force will, well, let's do this. Let's walk our way through it. So all we're going to do is shift the equilibrium to a new position, okay? We're just going to say that instead of this point being my equilibrium point, like it would be on a horizontal surface, okay, so if I put a mass there and it's at its normal length, that would be like this setting. But if I let this hang down now, all I'm doing is shifting my equilibrium force. And that will be at the point at which the restoring force from this point to this point will be in equilibrium. So this is going to be mg, right? Right?
Yeah, sorry.
Okay, and this is going to be my restoring force. And so this is going to be negative kx. And so what we're going to do then is say at this point then, so you're absolutely right. In this sense, we do add in gravity.
Yeah.
Okay, but at that point, you would agree that gravity is balancing the restoring force of the spring, right? Yeah? So it's going to be force, the net force is going to equal 0 because it's not moving, right? It's not accelerating at that point. And at that point, the weight is going to equal the restoring force. And this is the restoring force for this equilibrium point. Okay? This is the restoring force for this equilibrium. Okay, we've got a new equilibrium down here, but the x that we're talking about for this point is going to be the distance that the mass pulled it down. Okay, so mg is going to be positive, and this is going to be the restoring force holding mg in equilibrium. That's going to be negative. X0 is the new equilibrium point from which everything else is measured.
Do we ever need to know the original? Like, does that actually matter for
You could be asked to figure out what the original point was. Okay? So you won't need it to know it in terms of it'll help you find something else, but you may be asked to find what the original point was. Okay? So x0 is going to be the new equilibrium point from which everything else is measured, and that will be a certain distance from the original equilibrium point. Okay? So the difference in the original x equals 0 and the new x0 is given by, since I've got a balance here, right? These two forces are balanced. I can say that mg equals kx0, and I can find out what that original point was by dividing mg by k. So whatever that original point was, where it's just sitting there, and now it's hanging by a mass, this distance this x0 is going to be given by mg divided by k. Okay, so if I do need to find it, that's how I would find it. Okay, and it's just a matter of remembering that at this point, these two forces have to be balanced, and if you set them equal to each other, you can solve for that x. Okay? Even though we have a new equilibrium point, the same k can still be used. Okay? The spring constant doesn't change just because it's stretched, right? It's going to be the same no matter what. So I can still use that k. And so we have a problem here. When a family of 4 with a total mass of 200 kilograms step into their 1,200 kilogram car, the car's springs compress 3 centimeters. Okay? What is the spring constant of the car's springs, assuming they act as a single spring, and how far will the car lower if 300 kilograms is added rather than 200 kilograms? So before the weight of the car is ever added on to the springs are at their natural point, right? So I've got my springs here, and they're sticking up from the wheels. And we could say that this is the original 0 point. At this moment, they're compressed by 0 amount, and the restoring force is going to be 0 newtons. Okay? So I have no weight on them. I do know that g is 9.8 meters per second. I know that mass is 0. And I don't know what the spring constant is at this point, but I know that x is 0 and negative kx is also 0 newtons. Okay? When the mass of the car is added, the springs are compressed. In this case, we aren't told by how much, but we don't really care because we're going to treat this as if it's the new equilibrium. Okay? That's our new normal, our new equilibrium. Okay? Doesn't matter, and that gets back to your question, DJ, do I need to know that original point? For a problem like this, no, I don't really care because this now is my new normal point. Okay? So we're going to treat this as if it was the actual equilibrium point, even though the springs are now partially compressed. Okay? And now that I know that the mass is 1,200 kilograms, the car, I know that the weight is 11,760 newtons. Therefore, because it's balanced with the restoring force of the spring, I know that that's negative 11,760 newtons. Okay? But I don't really care what that is.
Wait, why is it equal?
Because it's not in motion. It's not accelerating, right? Once it comes to rest on the springs, it's not accelerating, is it?
No.
So the weight must be balanced by the restoring force of the springs.
Oh.
Right?
Yeah.
Does that make sense?
Yeah.
Okay. Okay? So we're treating this as our new 0 point. We can ignore the mass of the car in the above problem. It doesn't matter because that's our new 0 point. And all we need to do is consider the mass of the people. Okay? They have a mass of 200 kilograms. They compress the spring by 0.3 meters. And we know that the force causing this compression is 1,960 newtons. It doesn't matter that the car is already compressed it a little bit. That was our 0 point, or our new 0 point. Now we've added the people. They have 200 kilograms of mass, and their weight is 1,960 newtons. So my new restoring force is negative 1,960 newtons. And so now, since I know that the displacement is 0.03 meters, I can find what that spring constant is. Okay, so all I would have to do is divide by 0.03 meters, and that would give me the spring constant. Okay, so get comfortable with this idea that once I have an equilibrium position, I can treat it as if that's a 0 point. I can treat it as if anything else I place onto the spring is a new problem. Okay? I don't have to worry that the springs are already compressed by 11,760 newtons because it was at an equilibrium point. That was my equilibrium point. Now I've added this new 1,960 newtons, and I can just treat it as if it were a brand new problem. Okay? So I don't really have to worry about that, and I can find out that since mg equals kx0, the k is going to be that 1,960 newtons divided by 0.03 meters, and so my spring constant is 65,333 newtons per meter.
Are we ignoring the negatives? Did you already say that? Can't remember.
Which negative are we?
Negative kx.
Okay, I've got the negative here, but then in order to set these equal to each other, I just added it to the other side. That
Sure,
made
our
it-
answers ever be negative in this situation?
Huh?
Sure, our answers would be negative in this situation?
No.
Okay.
And you would never, if you somehow managed to get a negative for value for a spring constant, I'm not sure how you would do that if the signs were correct, but the spring constant always needs to be a positive value, so you've probably switched a sign around there somewhere if you've got a negative value for a spring constant. Okay? And then all we would have to do then to figure out how far the springs would be compressed if we had 300 kilograms instead, remember that force equals negative kx, and we would have that spring constant now, negative 65,333 newtons. Whoops, let's isolate it first. X equals F over negative K. And then we would have 300 times 9.8. Somebody multiply 300 times 9. It's, what is that going to be? 27. 29.
2940?
Is it 2940 or 2960? It's
2940.
It's 2940. Okay, so 300 times 9.8 is going to be 2,940 newtons. For the 300 divided by the 65,333, and so that force is going to be in the negative direction. We'll cancel those out. And how many meters will that give me?
1 over
2940 over 65. How much?
20.
0.045. Okay? So now we would have it compressed that much. Okay? So I think that was,
Was it 0.04 or point? On 0.
okay? And then if we wanted to, now that we know the spring constant, we can go back and determine how far the springs were originally compressed when the weight of the car was placed on them. Since we know that K now equals 65,333, we could go back and put that number of newtons in and divide by the spring constant. And the original weight of the car compressed the springs 0.180 meters. So that would be the way that we would find that original distance. Okay. So let's take a couple minute break, and
I hope